Okay, guys. So today the plan is I'm going to talk about formal power series and then generate functions and then walk generate functions. Now, again, I'm talking about what people call formal power series. I don't think anybody knows what the word formal means in this context. It probably just means different from what they're used to thinking about, but we won't go there. So I'm going to give a definition. So we've got to be a little careful. The thing that causes issues is using this formal sum notation. Okay, but I'll come back to that in a moment. So a formal power series of a ring for us is simply a function from the non-negative integers to the ring R. So it's just a sequence of elements of the ring indexed by the non-negative integers. Okay, now it's traditional to write these in this form. And once you get used to it, it's okay. But the problem, it's similar to the problem is this sum is not defined because it's an infinite sum. And to define infinite sum, you need limits. And there's no limit in sight at this point. Okay, I've just given you the definition for a power series. I've said it's a sequence. And so you can, if you choose to write this, what you're indicating here is that your sequence is going to consist of things A sub k, where k goes from 0 to runs over integers. Now, the ring R could be any field, or it could be the ring of matrices over a field. And when it comes to fields, don't always assume that you're dealing with some field of complex numbers. It might be the field of rational functions, for example. And that comes up, you do deal with that, whether you realize it or not. We'll come back to that. So the terms of the sum are elements of the polynomial ring. Okay, there. So we have no trouble about terms of the sum. What I'm objecting to, what the issue here is that this doesn't mean anything because I haven't told you how to calculate. But I mean, the usual definition of sum is it's a limit of a sequence of partial sums. And so you need to say what limiting operation is. And you can do that, we'll get to that. But anyway, so power series is just a sequence of elements of a ring. And we ask questions about what's the nth element, what's the third element, and what's the constant term. That's the sort of questions we ask. Now, any polynomial over the ring is a power series. Okay, you just take the coefficients. And in a certain sense, this is the way that your instructors in your undergraduate courses think about polynomials. They just think of it as a sequence of powers of x, or linear combination of the powers of x. The students tend to think of these things as functions, which is what causes problems. And the same thing is happening here, because if we talk about power series, you're conditioned to think of them as functions, and their job is to approximate some other function, but we're not thinking of them as functions. Okay, they're just sequences. So we get these, so we get a power series, just think of a sequence, we can add two sequences term by term. So that gives us an addition. And there's a multiplication, which is the multiplication used for polynomials, and I'll write that explicitly in a minute. It's very useful to have a notation to pull out, if we have a power series A of t, then I'm going to write square brackets t of k, comma at to be the coefficient of t to the k in that series A of t. So in the term A before, that would be a little a sub k. Okay. Your life is a lot easier if you have this operation around, okay? And you can think of it as kind of a linear functional that helps you, but we'll leave it at that for now. But so this is useful. So I'm going to give two examples, so to speak. I've already told you how to do the sum of two power series. You just sum the coefficients term by term. Okay, and in a certain sense, this is the definition. The problem, as I said, there's an minor issue, well, an issue which we'll resolve with these sums, but that's now the product rule looks a bit of a mess, but it's just the products that you use for polynomials. Okay, and so if you can add two polynomials and multiply two polynomials, then you can do the arithmetic in the power series. So the power series over R form a ring because you can add them and you can multiply them, and the series which takes A0 equal to 1 and everything else 0 is an identity under multiplication. So it's even a ring with identity, as our rings would normally be. So we add them and we multiply them and we extract coefficients. And now We also take constant terms, which is sometimes you can almost just a correcting coefficient, but it's a constant term that matters. We are not going to try and compute the value of A of t when t is equal to 3/2. We're just not interested in that question, and we don't need it. So you could think of it as a bag of coefficients. Now, I do want to make sense of the sum notation, the sum notation here. And so for that, we have to go further. So I'm going to find the order of a power series to be the least integer I such that the coefficient of t to the I in the series is not 0. So it's the exponent of the first non-zero term. And now then I'll define the norm. Should give myself some colors here. The norm of the series is just 2 to the minus the order. So if you think of your power series as being a function of x, and you think of x as being small, then in some sense, small power series have small norm. Now, I don't want you thinking of power series as functions, but it helps in this case. The other point is there's nothing magic about the choice of t here. Any constant greater than 1 will do. Okay, and so the intuition is that if you've got a series and the first non-zero term has got a large exponent, then that is a small series. Because we're focusing on the left-hand end, and so stuff that goes off on the right-hand end, we're trying to ignore. And now the key point is that this thing I've introduced here called a norm is a norm in the normal sense of the word that you would have learned in analysis. Okay, it's non-negative. If the norm is 0, then the series is 0. You've got a now in this case, what happens if alpha is an element of R, not 0, then its norm is 1, and so you get this property, and you also get the triangle equality. Now the point is you get something stronger than triangle equality. You get this inequality, which implies triangle equality. The norm of this property is called non-Archimedean. It's not entirely clear to me why, because I'm pretty sure Archimedes had absolutely nothing to do with it and never thought about a norm on the vector space. But anyway, so it's a non-Archimedean norm. And so this condition here is stronger than the triangle equality. And that has some makes some things easier for us. But so it is a norm. And so everything you did in analysis with the norm, we could do with this norm. Okay, so now I can define these sums, sigma a sub k t to the k. Okay, because I've now got a sequence, I can take the partial sums, I've got norms, and then I can talk about convergence. But it's convergence in this power series norm. Now, a similar norm to what we're using here comes up in number theory when you're dealing with so-called p-adding norms, but you probably haven't run across that. But in number theory, they use other norms. Okay, and so we'll come back to that. Now, this is basically a simple remark that the order of a product is the sum of the orders, which implies that the order of fg is less than equal to the norm of fg is less than the norm of f times the norm of g. So technically this means this is an algebra norm. So we don't just have a vector space with the norm, we can multiply things. And so now we've got an algebra of the norm. And so this gets a little more complicated because if you're careless, your ring R might have divisors of 0. And so we'll try not to make that mistake. So our rings will usually, I mean, the worst ring we're going to deal with will be the ring of matrices, n matrices over a field. Okay, so we'll have, and so in particular, go back a bit, these A sub i's could be matrices. Well, you'll see the examples as we come, but that's okay. Now, when discussing talking about generate functions, usually the tradition is just to sort of say power series just work the way it used to and go straight on, and students can get puzzled. And so what I'm trying to do is to convince you that there's a rigorous background. I'm not trying to go through and actually derive it all, but let's throw some nasty words at it. So we have a metric space, so a vector space with a norm on it. Then a sequence of elements is Cauchy if for each real positive epsilon, there's an integer n such the difference of the m and nn is less than epsilon if m and n are greater than n. Okay, so that is a Cauchy sequence. Okay, now Cauchy sequences are important because the Cauchy sequences of rational numbers are the real numbers. So there are a couple of ways of constructing real numbers, but for anything I've ever done, the best one is in terms of Cauchy sequences. Cauchy sequences come up in lots of places. And so you just take Cauchy sequences. Now, I said you use Cauchy sequences to define it. There's obviously a bit more to it than that. And I'll do that, cover that too. So two Cauchy sequences are equivalent if their difference converges to zero. And the equivalence classes of the Cauchy sequences give you the completion of your vector space with respect to the metric. Now you don't need to worry about metrics, all our metrics will be norms. Okay, so the point is once you have a norm, you can define Cauchy sequences and then you can define completions. If you do that with the rational numbers and the ordinary absolute value, then you get completion, and that completion is the real numbers. And that's probably the slickest construction of the real numbers. I don't like getting to cuts very much. So the statement we need is that the ring of formal power series, which is usually denoted by R double square brackets T, is the completion of the ring of polynomials R of T. So power series have the same relation to polynomials that real numbers have to rationals. Okay, and every real number is a limit of rationals, and every power series is a limit of polynomials. And this means practically that most things you can do with polynomials, you can do for power series without any more thought. Okay.
I'm sorry. Can you remind me what was the metric on the?
Sorry, I can hear some noises, but I can't hear what you're saying.
Can you hear me? Hello. Can you hear me?
Try again, please.
Can you hear me now?
Yes.
Okay, so my question was, can you remind me what was the metric on polynomial ring with respect to which
the metric is the one I defined before in terms of the order.
Okay. Okay.
Yeah. So I defined it on power series, but every polynomial is a power series, so I defined it implicitly for polynomials as well.
Okay, thank you.
Now I've never seen anybody use it just for polynomials, so but yeah. So and in a certain sense, to work with this, you just need to sort of, if you accept the idea that power series are limits of polynomials, then you can work with them the same way you work with the reals. Okay, so that you can always sort of go back to that. I wanted to give a more formal description of the completion. I'm not quite sure why. So let's suppose we have a ring, then the sequences, the sequences of elements of R is a ring under the multiplication that I've given you, and given a metric on this space sequences, the Cauchy sequences form a subring. So you've got sequences, you've got Cauchy sequences. Clearly, the Cauchy sequences are a subset of the rings. Now, the Cauchys, they form a subring, so the Cauchy sequences are closed under multiplication addition. That needs proof. It's not difficult. It's just it does need proof, but I'm not going to do it. So the Cauchy sequences form a subring, and the Cauchy sequences that converge to zero form an ideal ring. So you can take the quotient of this ring by this ideal, and then what you get is a quotient of a ring over an ideal. It's a ring, and that ring will be the completion. Okay, so that's a formal description of the process. I'm not, as I said, I'm not trying to give you a careful presentation of the theory, but I've given you enough information that you can actually check. In principle, you could go and check that power series are completions of polynomials. Now, as I said, the metric or norm we're using for the power series satisfies this stronger version of the triangle inequality. And one consequence of this is some of the problems you have in analysis go away. If you have a sequence of power series that goes to zero, okay, in norm, then the sum is defined. Okay, so over the reals, the sum 1 over n is not defined, it's infinite. But for polynomial or for power series rings, if your power series go to 0, then the sum is defined. Okay, so that's an advantage of working with non-Archimedean norms. Well, I guess I'm going to call that an exercise at this point, aren't I? I want to give one illustration of using this. Suppose I have a power series with constant term 0. Now, you'll see quite often when I'm trying to do calculations with power series, I need to fuss about the constant term. Sometimes I want it to be 0, sometimes I want it to be 1. But in this case, I'm assuming it's 0. Then this series, well, the norm of 1 is 1. The norm of f is 1/2. The norm of f squared is 1/4. Okay, so the norm of f to the k, the norm of f to the k is going to 0 as k goes to infinity. So this sum is defined. Okay, and it's the multiplicative inverse of 1 minus f. You just multiply it out. You can make it look a little more careful, but you multiply the two sides together and you get the identity. So a power series, it follows that a power series is invertible if the constant term is invertible. Okay, and so when we're working combinatorially, we often want our coefficients of our ring to be the integers. And so in that case, the constant term will be 1. If the constant term is 0, though, we can always form the inverse. And that's a consequence of this fact, which I guess I'm effectively going to leave you as an exercise. And actually, that reminds me, as an administrative announcement, put it on the webpage. But if you're going to if you want to hand in solutions to from the first 14 questions, they have to be handed in by the 5th of February. That's 2 weeks from today. Okay. So one reason is I don't want people working on the old stuff when I'd like to be working on assignment questions related to what we're discussing in lectures. Okay, so if you're going to hand in questions from one of the first 14 questions, it has to be handed in before the 5th of February. If you've already handed stuff in, don't worry. Okay, if it comes back to you, you can still resubmit. But if you're handing stuff in late, we're not going to be getting too many resubmits. I don't want people handing in messy stuff and then using it as an excuse. So the idea is, there are plenty of problems there to do. Okay, so the goal is just to get you to move on to onto newer problems. Okay, and so the short summary is, okay, if you want to hand solutions to questions 1 through 14, they have to be handed in before February the 5th. That's 2 weeks from today. Now, I will close off some of the other ones. Probably it's about the next 15 will be the next ones to be closed off. Okay, so that kind of get your team, but there's not going to be any shortage of problems to choose from. Are there any questions about that? No. Okay. Okay, so any questions about power series now? Okay, so the short version is that if you pick the right norm, the one that I'm using, then you can work with power series the same way you work with power series in general, the same way you work with power series, convergent power series in analysis. Okay, so you don't need convergence to get the properties. You can define all these things in general, and well, they do converge, but they're converging with respect to a different norm. Okay, so anyway, since no question, that's it for power series. So now I want to talk about generating functions. These are often called, or sometimes called, generating series, which is slightly better because whatever these are, they're not functions. But so anyway, the term generating function is fairly standard, so I'm sticking with that, whether I like it or not. So a generating function is a power series where the coefficients in general count something combinatorially interesting, or maybe something interesting in statistical physics. Okay, so the coefficients of a generating function would normally be non-negative integers. Now, I'm not sure that there is a formal definition of generating function anywhere, but you can think of it. So basically, two things: the coefficients of the series are going to be non-negative integers, and Secondly, they're going to have be of some combinatorial interest. Okay, and so then the problem is to relate properties, algebraic properties of the series, to properties of the combinatorics you're dealing with. Okay. The other issue I need to deal with is I think a number of courses that will teach generating functions start by writing down recurrences and then using generating functions to solve recurrences. And that is not an efficient way of working with them. And it's not what they're for in a certain sense. Okay, you can use them to solve recurrences, but there are other things you can do. And generally, if you're trying to work out what a generating function is, setting up a recurrence is not the right way to start. But okay, so I'm giving a sort of more concrete example here. So we're going to pick a set omega. It could be, for example, for a set of all strings formed from the symbols A and B. Now, one comment here, when I'm working with strings, there's also going to be the empty string in general, which we usually denote by epsilon. So this is just all words you can form from A and B, including the empty word, which is epsilon. Now, the thing that confuses everybody is we have to define the generating function, we need to introduce a weight function. And everybody asks what the weight is. And well, the two answers, I don't know. And in a certain sense, it's your choice. Okay, so in terms of a string, it could be the length of the string, or it might be 3 times the number of A's in the string plus twice the number of B's. It's just some function which for some reason is of combinatorial interest to you. Okay, so you have a weight function. The requirement here is that the weight is always takes non-negative integer values, and that there are only finitely many strings with a given weight. So length is a good example. There are only finitely many, there are 2 to the n strings of length n. Okay, and it's not negative. And so then you define this sum to be your generating function. So you have some things which you're interested in counting. These things have a weight or a size or something along these lines. And so you can, and the number of things of a given size is finite. Then you can write down this sum, and this is a generating function. And it's a power series. And so, as I said, the idea is to try and look at the relation between the algebraic properties of the series when they factor and properties of the things, your combinatorial things you're working with. And you'll see that in detail as we go on. So this is a generating function. Usually I could say generating function for omega, but on the first occasion, I want to make clear it depends on the weight you choose. Okay. Now, as I said, well, the strings are a good example. There are more complex examples, but the strings are a good example. So you can think in terms of strings. And so you can assign weights. You can even have 2-valued weights. You might say T to the number of A's by S the number of B's, but we won't be going there. Now, how do we work with generating functions? Well, there are 3 rules, which I call the sum rule, the product rule, and the sequence rule. Okay, and using these 3 rules, we can compute generating functions for lots of different setups. Okay, and again, you'll see the examples as we go on. Okay, now these are reasonably straightforward. So the sum rule, well, it's more or less simple. If you have 2 disjoint sets, omega 1 and omega 2, with weight functions, weight 1 and weight 2, then I can define a weight function on their union to be just the weight of alpha is the weight in here if it's in alpha 1, and the weight in here if it's in alpha 2. So this is now a weight function. It's not negative, and the finite condition holds. And so I have a setup. I have a set omega and a weight function weight, and so I get a generating function. And that generating function is just the sum of generating functions for omega 1 and omega 2. Okay. Now, so the product rule is very similar. In this case, we're dealing with the Cartesian product of the 2 sets. Okay, and now we're defining, in this case, the weight function on the product is given by the weight of the first coordinate in its set and the weight of the second coordinate in its set. And again, if we have the generating function for omega 1 and omega 2, the generating function for the Cartesian product is just the product of generating functions. Okay, so we have a product. So if we can decompose the things we're trying to count into two classes. So let me say that I have a graph with X. I have a graph X with a vertex A. And I can think, I want to look at the walks in the graph which start at the vertex A. Okay, so a walk is a sequence of vertices where consecutive terms are adjacent. And so the length of the walk will be one less the number of vertices. So a vertex by itself is a walk of length 0. An adjacent pair of vertices gives you a walk of length 1, and so on. So we have walks. And so I have an infinite sequence. I have infinitely many walks in this graph, of course. Okay, now I can partition the walks according to the vertex, their last vertex. Oh, damn, what's doing this? According to the last vertex. And so so my graph's got 5 vertices, then I've got 5 choices. So that I'd partition the walks into 5 sets. The walks from A to A, the walks from A to B, the walks from A to C, and so on. And so then the generating function for all walks would be the sum of those generating functions. Now that's not a particularly useful statement, but I mean, it's true. Okay, and so often when you look at a situation, you can divide the things you care about into classes, and then you can work with each class separately. Now, okay, I could also consider closed walks, which start. I don't know what's going on today. Which start and finish at the same vertex. Well, that's all right. I mean, I can't do that partitioning I just spoke about, but I've got an infinite set of walks. But if I have a closed walk, actually I want to do this different color, it wanders off and will eventually come back. Now, it can stop at that point, or it may decide, no, it's bored, and go off and do some more walking. Okay, now what's happening here is that the first blob I drew here in red is a closed walk that returns to A exactly once. And as I said, if we're not happy doing that, we go off and do it again. And now we have a walk which returns to A exactly twice. So every closed walk can be partitioned uniquely into closed walks that return exactly once. Now, so what we have is we've decomposed our closed walk into a sequence of closed walks return exactly once. And we have a rule for dealing with that, and that's the sequence rule. So the sequence rule is if you're counting sequences from omega, and no element of omega has weight 0, then the generating function for the generating function of sequences is 1 over 1 minus A. Now, notice I want omega to have weight 0. This implies the constant term of A is 0. And so this is A, I can think of A as X times something, but the point is this inverse exists because A has got norm less than 1. Its constant term is 0. Okay. And so it's not customary to note this by putting a star on something. So I don't know what W is in this context, but this would be the generating function for sequences. Okay. So there are 3 now. The sequence rule is actually a consequence of the product rule. Okay, plus a simple induction, very simple induction argument. So, but the point still is, you can, if you're trying to solve a counting problem, then this is telling us there are 3 things we can do. We can try and divide things into classes, disjoint classes. We can try and represent the things we're dealing with as ordered pairs, or we can think of them as sequences. And all these are useful. And the goal is that if you're trying to get a generating function, the first thing you should try is to get it using these rules. Okay, so let me do a few examples. So I should make one more comment. If you're working with strings, the issue is you're going to use the product rule, and you give me an element in my set. I have to be able to divide it into 2 things in a unique fashion. Now, sometimes when you're working with strings, you might decide it can get more confusing. So all I'm going to say is sometimes the rule for strings could cause issues. I don't think it's going to cause issues for us because I'm not really going to be working with strings very much. But having said that, let's look at some examples. So I'm taking the alphabet of two symbols A and B, and I'm declaring the weight of A and the weight of B to be 1. Now, the point is that you get to choose the weight. Now, normally there's an obvious choice, but I mean, it is your choice. Okay, so in this case, I've chosen both be 1. So the generating function for omega is just 2 times t. There are 2 elements of weight 1. Okay, the generating function for the sequences is 1 over 1 minus t, which is the sum of 2 to the k times t to the k. And that's, of course, what you expect. There are 2 to the k sequences of length k built from A and B. So that's the product rule. Now, the second example, I'm going to take the same set omega, but I'm going to take a different weight function. I'm going to take A to have weight 1 and B to have weight 2. Now, the way to think about this is you have a string of length n, and you want to cut it into pieces of length 1 and length 2. How many ways can you do it? Okay, now the generating function for omega in this case is t plus t squared, because you have 1 element of weight 1 and 1 element of weight 2. And so the generating function for the sequences is 1 over 1 minus t squared. Okay, and as a very mild sanity check, you can see that the constant term of this generating function will be 1. Okay, as it should be. Okay, so the comment here is that the coefficient of t to the k is the number of ways we can write k as a sum of a sequence of 1s and 2s where the order matters. Now, the point about getting the generating function is, well, you know, it's all very well I've computed the generating function. What does it tell me? It tells you quite a bit. And the first thing I want to note is we can get the coefficients out. So the coefficient of t to the k is a solution to a counting problem. Okay, and so how do we get the coefficient of t to the k? Well, we use our notation before. We want the coefficient of t to the k. Well, we first note that we have this identity. And so I'm going to look at the coefficient of t to the k in this. Now, the point to notice about, okay, so if you think about it, you take a 1 times the coefficient of t to the k and you get an a to the k. If you take t times the coefficient of t to the k minus 1, your coefficient is a to the k minus 1. If you take t squared times the coefficient of t to the k minus 2, you get an a to the k minus 2. So the coefficient of t to the k in this series is given by this. Okay, assuming k is at least 2. You've got to pay a bit of respect to your initial conditions, but k is at least 2. Now, the point about this, oops, that's not what I meant to do, is it? I'll be back, don't worry. The point about that I wanted to make is that this is a power series. Okay, and we're saying it's equal to 1, so its constant term is 1 and all its other terms are 0. And so we deduce that, so we deduce 2 things. The first thing, well, I should have actually written it in. This implies, not doing that color, it implies a to the k is equal to a to the k minus 1 plus a to the k minus 2, k at least 2. Okay, and it also implies that, well, A0 is equal to 1, and your problem is to work out what A1 is. Once you have that, you can then compute a to the k for all k. But the point here is that the answer to this problem is the Fibonacci numbers. Now, that's why I picked it, of course, but I mean, the point is so from that series, you can get a recurrence. This generally works best when your generating function turns out to be equal to a rational function. Then in that case, there's a machine whose handle you can turn. But the point is, from the generating function, you can extract the recurrence. Now, the generating function also gives you other information about the rate of asymptotic growth and things like this. So there's much more information in the generating function than there is in the recurrence. if I want to prove that Fibonacci numbers grow exponentially, I can do that easily from the generating function. It's more trouble to do it from the recurrence. Okay. I just wanted to show another way of looking at these problems. This is, again, I'm sticking with the Fibonacci number. If you've got a sequence problem, so you've got a linear recurrence of finite order, sequence satisfies it, then you can write it in matrix form. That's what I've done here. So a to the k is a to the k plus a to the k minus 1, and a to the k is a to the k. So that equation describes the recurrence, and I don't like that mistake. And hence, if you think about it a second, you get that we get a formula that a to the k plus 1, a to the k is a to the k times the initial values, a1 and a0. Now we're trying to compute a to the k, so I don't need the full matrix. I don't need it. I just need the bottom entry of this vector. Okay, but I can get that by computing powers of k, computing powers of a. Now you can do that by something which functionally looks like the spectral decomposition. You've got to be a bit careful because in general, this matrix you get won't be diagonalizable, or at least it won't be symmetric. But the eigenvalues tend to be simple, which is enough. So the point is you've solved the recurrence by doing that. Okay, and if you go a bit further, I can now take this sum, and I get that sum is equal to this. So I get a formal expression, so that the bottom entry, which is what I care about, is the bottom entry of this. Now, I minus TF inverse, you can invert. It's 1 over 1 minus T squared times this. So you can get it. My point here is by writing a linear recurrence as in terms of matrices, you get a lot of, you can go a long way. But the other comment I want to make here is that this is a generating function. Well, certainly a power series. The coefficients are 2 by 2 matrices of integers. Now, you've got to be a little bit careful here too. The point is we're working with the matrix 1 minus T times F. So we're not working with matrices over a field. We're working with the matrices over the ring of polynomials in T. Now, one piece of advice is if you can avoid it, do not do linear algebra over anything other than fields. Okay, it gets very messy very quickly. One way you can sort of recover your grace here is to say, well, I won't work over the ring of polynomials in T, I'll work over the ring of natural functions, that's the field. Okay, so when I try and compute this matrix, I've had to divide by 1 minus 2 minus T squared. So this is where my rational function is coming from, not just a polynomial. Okay, okay, I think that's enough on that. Yeah, so the summary here is, okay, we can compute generating functions using the sum rule, the product rule, and the sequence rule. We can, and from the generating function, we can derive, generally speaking, we derive a lot of information. The thing to bear in mind here is, in a sense, what does it mean to solve a counting problem? Okay. You would like an explicit formula? Well, you can work that out for Fibonacci numbers. There's a sum of powers of alpha to the n plus beta to the n, specific alpha and beta scale somehow. But so you can get an explicit formula, but then someone might ask you, how fast does this grow? Or when is this? When is the Fibonacci Fn odd? Okay, there are a lot of questions you can ask, and just getting a formula is possibly not what you wanted. If you're working with, if your counting problem is arising from analyzing some algorithm, you probably care more about the rate of growth than the actual value of the coefficients. You want to know whether your algorithm runs in polynomial time or constant time or exponential time. And if it runs in exponential time, what's the constant? So in solving a counting problem, there are a lot of questions you could be asking, and it's not always just come up with a formula. Okay. Sometimes what you need to know, you get a generating function, and you got a generating function. You want to think, you actually want to know what the radius of convergence of the power series is. Now, this doesn't fit in the framework I've been talking about up to now, but this comes up more in statistical physics. Well, in other places too. But so the point is, there are lots of questions you can ask, and in most cases, you can work out what you want from the generating function. And if you can't get the generating function, you probably can't answer the other questions anyway. I mean, most counting problems can't be solved in a certain sense. You can't find a generating function, you can't find a formula. Okay, but there are lots of interesting cases we can solve, so we pay attention to those. So after that, any questions? Okay, now for this course, I'm not really concerned about Fibonacci numbers, although they will come up again. If I could. Interested about generating functions related to walks and graphs. Now, I already gave you one quick example. So again, a walk in a graph is just a sequence of vertices with consecutive vertices adjacent. Okay, it's not a subgraph because the walk can use an edge more than once, and it can use vertices more than once. Okay, so it is just the only conditions are it's a sequence of vertices, and the nth vertex is adjacent to the n minus 1th. Okay, now the place where walks come up is when we're thinking of powers of the adjacency matrix. The ij entry of a to the k is the number of walks in the graph from I to j with length k. So if you fix I and j, then I can write down a generating function whose coefficients are just the numbers of walks from I to j of each length, and I get this, which is a generating function. But now you notice I've got I and j there, and there's nothing here special about I and j, so it's in a sense more natural to work with the full matrix. And so I'm going to define wxt to denote the inverse of I minus ta and call it the walk generating function of the graph. And that's the function I want, because it solves all these counting problems. Now the proof, I think I've got some notes coming up. So the proof that this is a number of walks is a simple result using induction. Did I? Well, I want to cover something else first. So this is the walk generating function, and that's what we'll be using when we work with our quantum walks. We'll be in a lot of our spectral stuff. We're using that all the way along. Okay, so it plays a very important role. Now, the related matrix, which is Ti minus A, and I tend to use the two equivalently, is formally called the resolvent of A, and it plays a very important role in spectral theory. So interdimensional operators and things that they deal with resolvents. And this is in some sense, so it's interesting that the walk generating function is important for what we're doing with the walks, but the same thing is important for spectra of infinite operators. Now the excuse me, it's warning me to. So if the eigenvalues of A are θ1 to θd and corresponding idempotents E1 to ED, then I can form the spectral decomposition of Ti minus A inverse, and it's this. Okay, so I can expand the resolvent as a linear combination of the idempotents, and so we get the formula for the ij entry. It's a number of walks in the graph. Generating function for walks in the graph from vertex I to vertex j is given by this. Well, this is a rational function. So we've got a partial fraction expansion rational function. It depends on the eigenvalues and the ij entries of the idempotents. And so if you have the idempotents explicitly and the eigenvalues, you can sort of solve any counting problem to do with walks. Now, walks of some interest in the source also, sometimes you can take some combinatorial problem and translate it into a problem about walks on a graph or direct to graph. Okay. For our purposes, we're going to be, when we work with continuous quantum walks and discrete quantum walks, we're going to be fussing a lot with powers of A. Okay, so that's why we need it. Okay, so I said again, a walk is closed if the first and last vertices are equal. And the generating function for closed walks in the graph that started U is just the UU diagonal entry of the walk generating function. And I'm going to denote it by C for closed, C sub U of closed walks. And then the set of all closed walks is just the sum of these generating functions. So this is an example of using I guess this is an example of the sum rule. If you've got closed walks on a graph, you can partition according to their starting vertex. Okay, and by the sum rule of the generating function for all walks, this is the sum of the generating functions for closed walks. The sum rule was generally so trivial that you used it without noticing. With the product rule, you've got to be a little careful to make sure you get the right weight function. It's easy to make this, it's not easy to make a mistake. And I was talking about the closed walks return exactly once, and so I'm going to denote those by C sub U simple 1. And so they're the walks that return just once. And well, I could make it worse. We could also consider all walks in a graph which start at a vertex, or just generating function for all walks in the graphs. These could come up if we start talking about complements of graphs, but this is enough to go on with. So we have the walk generating function, which is I minus TA inverse, and then we have closed walks, closed walks that return exactly once. Now, what I've got here is writing out something that I stated before. Any closed walk that starts at U determines a unique sequence of closed walks that start at U and return just once. Now, the important thing here is unique. If you look at this, if I give you a closed walk that starts at U and you work out the partition into closed walk, return exactly once, you'll get exactly the same partition that I will. Okay, and so in that case, what we're looking at is sequences, and this process is reversible. If you give me a sequence of closed walks that return exactly once, I can concatenate them and I get a closed walk that returns to U. And so the sequence rule applies, and so we get that the generating function for the closed walks at U is given by this. That's the sequence rule. To count sequences, you have 1 over 1. Now, to apply the sequence rule, it's important that this has to have the constant term of this has to have coefficient 0, because you want the sum of the powers of this to converge. But there's no closed walk of length 0 that starts at U and returns to 0, and there's no closed walk of length 1 that start because there's no loops. So the order of this series is 2. Its norm is a quarter, and so there's no trouble with convergence. So the first non-zero term of this would be the valency times the t squared times the valency of the vertex U. Okay, and so my point is that now this will turn out to be quite useful. Okay, but my point is we get this relation with almost no work. We're not fooling around for recurrences. We're just saying we're going to say, oh, we're counting sequences. And the formula for sequences is 1 over 1 minus. Okay, so yeah, so a couple of things that, well, this is my first comment, that if the vertex U had the valency K, then this generating function starts with the KT squared. And the other thing is you can solve this generating function for C1 and express it in terms of C sub U. And there's a minor surprise in this. This is the generating function, so the coefficients are non-negative integers. So in consequence, the constant term of this C is 1. So the constant term of the right-hand side is 0. Okay. Now so what I'm thinking, the point is saying if you take the reciprocal of the generating function of closed walks, ignoring the constant term, the coefficients are non-negative integers. And that's not obvious. I'm not sure it helps me in any way, but it's something of a surprise. You wouldn't, I mean, you've got a power series, a generating function, C of t. In general, 1 over that is not going to be a generating function. The first problem is if the constant term of C was 2, then you're not even getting a integer coefficients. Okay, and the second problem is that the coefficients are probably aren't all non-negative, but they are, and that's a consequence. Although the other point is, I said that I was inclined. We have Ti minus U and Ti minus A and I minus TA. Okay, now I minus TA inverse is the walk generating function. I'm going to get a bit sloppy and start referring to Ti minus A inverse as the walk-general function. That's not quite true. And so the explicit relation is given by this. So the UU entry of Ti minus A is T inverse times the generating function for closed walks written out in terms of negative powers of T. So you can argue that the left-hand side is not a power series, but it's easy to deal with, and so I'll let you think about that. I'm not going to, this is a power series, Taylor series expansion about infinity, but so we get this relation, and so we need to go backwards and forwards, and this T inverse is just there so we can make nasty mistakes and get formulas wrong, as you'll see. The other point, the advantage of this is I can get this entry using Cramer's rule. I delete the U row and column, take the determinant of what's left over. Well, that's just the adjacency matrix of X, or Ti minus the adjacency matrix of X with U deleted. And then I divide by the determinant of Ti minus A. And so I get this formula that, well, the UU entry of Ti minus A inverse is given by this rational function. Okay, so this is an explicit expression. This is the generating function for closed walks in a graph that start at U. Sorry. That's the generating function for closed walks that start at U. So we've solved that. Okay. And, it's not too, it's not an unmanageable formula. I've written it out more explicitly here that in terms of the generating functions, I have to put in this T inverse. It's actually slightly cleaner if I bring the T's over there, bring this to the right and then replace T by T inverse. And so then the left-hand side is the generating function, the right-hand side is just a rational function. So that I don't really have to deal with power series with negative coefficients. Okay, for time. Okay. Sorry, excuse me. Yeah, we'll do this. We can do a bit more with the if the adjacency matrix says eigenvalues θ1 through θd with multiplicities m1 through md, then the trace of beta k is given by this formula. It's just the sum of the multiplicity times the kth power of the eigenvalue. And now when you multiply this by t to the k and sum, then the left-hand side is going to be the generating function for closed walks, because the trace of eta k is the number of closed walks of length k. And the right-hand side is this. Now, this is a rational function. You've got an explicit form that just depends on the multiplicities and the eigenvalues. So the left-hand side, well, okay, this calculation here, I minus Ti inverse, give me that, gives me this. Now, the point here is, well, it's this we can do something with. If P is a polynomial with 0 θ1 through θd and respective multiplicities m1 through md, then this partial fraction expansion of P prime over P is given by multiplicities over 2 minus theta. And that's on the assignment as an exercise, although it's an exercise from calculus. And so one consequence of this is that we get that the sum of the characteristic polynomials of the graphs x drop u, where u runs over the vertices, is the derivative of the characteristic polynomial. Now, we don't have much use for this, but it's still an interesting identity. Okay, so we're learning a lot about the walk-generating functions and the related polynomials, and we in particular have an explicit formula. Basically have an explicit formula for the generating function for closed walks. Okay, and the only thing we've used is Cramer's rule and what I was calling the sequence rule for power series. Okay, and I think that's where I want to stop. Yep, good. Perfect time. Questions?